Okay, so we are recording. Now we want to find the Taylor series for this function, 1 over the square root of x, about a equals 9, centered at a equals 9. So this is not a Maclaurin series because a is not equal to 0. So, okay, well, what we have to do is we have to do just like we did on the last problem. We have to find derivatives. One moment, sorry. Okay, let me show you the derivatives. So I'll let you copy them on the next page. Okay, so you're just copying down these derivatives. So you notice, and again, I'm not saying a whole lot of words just because, you know how to do derivatives. But as always, when I find a Taylor series, I have to get a pattern. Okay, hold on, I'll go back. One moment. Okay, you're good, yeah? Okay, you're welcome. You're welcome, Jonathan. All right, so of course, the 1 over the square root of x, I'm going to write that function. I'm going to write that function as x to the negative a half. And then I take consecutive derivatives. I usually go out to about 4 derivatives. And then I evaluate each of those derivatives at a equals 9. This is a hard problem. This is one of the harder problems. But I wanted to do it with you just so you could, see how it's done. See, you sort of figure out a pattern. Based on your terms, you figure out a pattern. So clearly this is an alternating series. Actually, I want to circle this. It's an alternating series. And we have some of the terms. Now, what would happen is in your in WebAssign for a problem like this, very likely it'll be a multiple choice answer. And again, multiple choice answers you have to be careful on because the limited tries. But you might see an answer that, oh wow, I mean, in other words, you can use the multiple choice to kind of help you a little bit in terms of like the answers they have, it can kind of help you figure out maybe what the pattern is. That's what I'm trying to say. So it's now that we have the function evaluated at 9 and the first 4 derivatives evaluated at 9, we're ready now to plug the function and derivative values into the Taylor series formula. That's what we want to do. And I'll go to the next page. Let me know when you're ready. Give me a thumbs up when you're ready, and we'll move to the next page, and I'll show you how I'll show you that. Are there any questions at all? All right. All right, let me go to the next page. Here then I put everything into the formula. Incidentally, let me go to the ebook real quick. Just go to that ebook. So now I'm using this formula. This is the general Taylor series formula. When A equals 0, you get the Maclaurin series formula. But this is the general Taylor series formula. And because A equals 9, not 0, we got to use that formula. Okay, so all I'm doing is I'm plugging in my derivative values, the values I got, and A equals 9 into the formula. And then that's going to get me what you saw. That's what you see here. Let me give you a moment to copy all this down. Let me know if you have any questions. And you notice the factorials here. Here they are. Okay, and then of course I'm putting in the There's f of 9. Here's the first derivative at 9. Second derivative at 9. Whoops. Third derivative. And fourth derivative. And the pattern appears to be then this series. This is the formula. That's the formula. So the 3 to the 2n plus 1 power, that means you're going to get like, well, yeah, you have like 3 cubed, 3 to the 5th, 3 to the 7th, 3 to the 9th. That's the 3 to the 2n plus first power. N factorial, well, that's just there. That's part of the Taylor series formula. 2 to the nth power, okay, we have 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. Okay, so 2 to the nth makes sense. You have to forgive me, class. I'm not here in this room alone. The person's gonna. Thank you, Elsie. Thank you. Now, you see here we have, we have 1. We have 1 times 3. We have 1 times 3 times 5. 1 times 3 times 5 times 7. That's going to be the 1 times 3 times 5, ... 2n minus 1. So this, I'm very confident in the web assign homework, you would have like, what do you call it? A multiple choice question, and this would be one of the answers. So, are there any questions on that? Notice I didn't ask about, for this one, interval of convergence. I'm just happy we got the power series, but we could always find the interval of convergence if we wanted. We could. So you've seen a few derivations of writing functions as power series. Okay, you've seen that. And it turns out that there is there's many functions, right? Well, this is a very general approach to writing a function as a power series. So long as the function and so long as its derivatives are defined, you can write the function as an infinite power series, as a Taylor series or Maclaurin series. Now let me show you another example here. I'll go into the ebook. Are we good here? Are there any questions? Yes, hold on. Somebody. Okay, who? Everybody's good? Okay. Okay. Let me. Okay. Let's see. I wanted to go. I'm trying to find the right the example I want to find here. Yeah, this is it. Okay, so the exponential function, e to the x power, okay, that has this Maclaurin series, e to the x power. Okay, I mean, that can be easily shown. They showed that in example 2. And the interval of convergence is actually going to be from negative infinity to infinity. But they do something interesting here in this. What they do, okay, is they talk about, this is something that will come up in section 8.8 actually. They mention that, okay, if you have this function e to the x power, and you want to, and you know it's Taylor series, you know it's Maclaurin series, well, you can write out what are called Taylor polynomials that are based on terms of the Maclaurin series. So the t sub 1 is 1 plus x. So e to the x power, if we were to, how many remember like linearization from calculus 1? If you take a function and linearize it, you find the tangent line approximation to the function. I don't know if you recall that, but that's something that's taught in calculus 1. Well, e to the x is approximately equal to 1 plus x. That's the linear approximation. The quadratic approximation t sub 2, that's a polynomial of second degree, is 1 plus x squared over 2 factorial. The third Taylor polynomial approximation to the exponential function is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, so those are, you know, when you take a finite number of terms of the series, you get a polynomial. And what they do in figure 1 is they graph the exponential function along with its Taylor polynomials, the first 3 Taylor or Maclaurin polynomials. Which polynomial, like, so if you look about the axis, if you look about the origin or the x-axis, look at the exponential function. These polynomials do a good job in approximating that exponential function up to a point, but then they fail, right? They fail. But which polynomial seems to do the best job over the widest range of x values? Would it be T1, T2, or T3? T1 is the black tangent line. T2 is the green parabola. That's the second degree Taylor polynomial. That's degree 2. And T sub 3 is the third degree Taylor polynomial. Which polynomial approximates the exponential function you think the best over the widest range? All right, Susanna's saying T sub 3, and that makes sense. That would make sense because the third degree Taylor polynomial involves more terms of the series. The more terms you take of the series, the better your polynomial approximation. So this is really a very, you know, and you see what we do in math is we often have functions that are very difficult to work with. They're what we call like sort of intractable functions. You know, you can't integrate them. You can, but if we can represent those functions as power series, then we can compute, we can approximate integrals and things like that. And you saw a little of that back in section 8.6. Now, there's a whole table. Let me just see if I can find this table here. It should be in here. Yeah, table 1. This is important Maclaurin series and their radii of convergence. So the ebook that has these formulas. So the first one should be familiar. 1 over 1 minus x equals that power series. That should be familiar. and the radius of convergence equals 1 for the first power series there in table 1. This is from section 8.7. The 1 over 1 minus x is equal to that power series, that geometric power series, over the interval from -1 to 1. So radius of convergence is 1. But the exponential function, the sine function, the cosine function, the arctangent function, those can all be shown to have what you see there, those results. They can all be shown to have that. Okay, are there any questions on that? So like you can use those formulas for your final exam. You can use those formulas to help you. Okay, you can use those formulas to help you. And in fact here, why don't we do another problem? Let's do another problem. I think we'll have time for it. Let me bring it up here. Okay, so section 8.7, we'll have to cover more of it. I mean, we're doing a pretty good job, but we'll likely cover more of it on when we return next Monday. But let's take a look at this problem. Let me give you a moment to copy it down. Mandy, that table is in your table is currently in your book, in your ebook. It's table 1, but I do have actually a handout I can share with you in Blackboard. I'm actually glad you asked that question. Go ahead and yeah, the handout. You're talking the final exam now, right? The handout that I'm going to share with you is a handout I created, and it would be for the final exam because it relates to section 8.7. Okay, so we're continuing here. So, okay, so we can, oftentimes what we have is we have a function like this, e to the 2x power times the log of 1 plus x squared. Okay, and we want to find a Maclaurin series for that function. Now, what we could do, of course, is we could find the derivatives, like the first 4 or 5 derivatives of this function, and then try to come up with a Maclaurin series. But that would be difficult for this particular problem because the derivatives are going to get quite complicated. So what would be easier to do would be to find the Maclaurin series for e to the 2x power and to find the Maclaurin series for the natural log of 1 plus x squared. Okay, that's what we want to do. And then we'll multiply those power series together. So there's a formula sheet here. This is a formula sheet that I will share with you. I'll make a note here to get it on, like when the section 8.7 course content That's section 8.7 in Blackboard, the course content. Section 8.7, all make it where there's a link where you can upload this document. But it has like the important Maclaurin series and their intervals of convergence right here. How many would like to download that? Is this a, how many think this is a, all right, Mandy would, all right. So, you know, of course the book is accessible, but yeah, this is a nice sheet. So, okay, no problem. No problem. So, course content. Okay, so there are two formulas we're going to utilize here. Jonathan, you will this formula sheet for the final exam, it will be there for you to download under supporting documents in Examity. So yes, you will be able to access this formula sheet. Yes, you will have it. But I like to give a very specific answer. You will have it. Yes. So here's the exponential function. And here is the natural log of 1 plus x. Now, I'm not worried about the interval of convergences for those functions right now. I'm just saying, okay, these are my two power series. Okay, now I want to go to the whiteboard. Hold on here. Okay, so remember what our function is. Our function was equal to e to the 2x, hold on, times the natural log of 1 plus x squared. Okay, now, e to the x, the power series, is this power series. Okay, that's from the table 1 in the ebook, section 8.7. This means then that this implies that if you want a power series for e to the 2x, all you need to do is substitute in 2x for x. That's all you need to do. And incidentally, if I write out some terms here, just writing out some terms here. I can write out some terms similarly for the power series of e to the 2x. See that? So you're using the Maclaurin series, a Maclaurin series, for e to the x power to help you get a Maclaurin series for e to the 2x power. See that? Are there any questions on that? 2 factorials 2, by the way. 3 factorials 6. Who's comfortable with that? Give me a thumbs up if you're comfortable, please. Who's comfortable? Well, are there any questions? Well, all right, let's look at the other function. The other function, second note, was, well, so we have the natural log of 1 plus x squared. So the power series for the natural log of 1 plus x is equal to this series here. It can be shown to be this series here. And this series actually is a series you saw back in section 8.6, I believe. Okay. All right, I'm just making sure everything's good here. Okay, and so this implies then, if I want the natural log of the series 1 plus x squared, all I have to do is just put in x squared where the x is. Okay. And so I'd have x squared. Let's make sure I'm writing this well. Minus x squared squared over 2 plus x squared cubed over 3, and so forth. Okay, so I have two now Maclaurin series, the two Maclaurin series representations that I need. Should have a plus here, right? Give me a thumbs up if you're okay with this. I'd like to at least have a couple thumbs up, or at least I want to make sure that this is like, I mean, okay, so like, think of it like this. Think of it like this. E to the x power is equal to this Maclaurin series. So if you had e, let's say you had e to the power cheese. E to the power cheese would equal the summation n equals 0 to infinity. And where the x goes, you just substitute in cheese. So cheese to the nth power over n factorial, right? If x equals cheese, you're just going to substitute in, x is a variable. Suppose x equals cheese. Okay, let's say that's x. You just substitute in cheese for x. Well, that's what I did with e to the 2x. 2x was my cheese. And for the log of 1 plus x squared is my cheese. Is that helpful? The cheese part. I'm not going to have a good vacation if I think you don't understand this. Gabriel, how are you feeling with this? Are you okay? All right, Susanna, I understand.
I'm
Victoria,
probably gonna
how
need
are
to
you
study
feeling?
a little more on this.
All right, Gabriel. All right. All right. Well, I'll tell you what, this might be a good place. I think this problem, what we'll do is we'll finish the problem when we get back next Monday from our, from Thanksgiving break. Uh, Basically, what we've done is we have been able to express e to the x, e to the 2x power and the log of 1 plus x squared, log of 1 plus x, the natural log of 1 plus x squared as Maclaurin series. And now we got to multiply them together. But I'm going to give you time to think on that. And I know you have a lot to think about now. You have your test. So let me stop the recording. We'll continue this problem in our next class on a week from today on Monday. We'll finish this problem up. Okay, let me stop here.